Ishara. No. Hello everyone, I am Bichunair. I am going to explain central forces in this video. So we see it now. Central forces. If we see the definition of a central force, a force which always acts on a body towards a point or away from a point, whose magnitude depends only on the distance from the fixed point. So that force is called central force. Okay, the central force always acts towards a point or acts away from a point. Okay, we can treat the point as a source. So here we are expressing the central force in this mathematical form, so which is shown in equation 1. So f of r is equal to minus del v of r minus dv by dr r cap. So that is negative gradient of potential, we can say. So the examples for central forces is gravitational force of attraction between two masses m1 and m2. So that is given by this equation f12, that is equal to minus g m1 m2 r cap by r square. If we see this, so it is a vector quantity what we are seeing here. So that is vector quantity. Now f of r, and it is a function of r, some scalar quantity, it is again a unit vector. So in place of small f of r, we are having 1 by r square here, and the remaining one is constant. So another example for central force is electrostatic force between two charges. Okay, F12 is equal to Q1 Q2 r cap by 4 pi epsilon naught r square. So here f of r is equal to 1 by r square again. So another example for central force is a force in mass spring system. F is equal to minus kx. So here f of r is directly proportional to x. Okay, these are the examples for central forces. So that means in case of mass spring system, the force always acts towards the point. That means if the spring is fixed to a rigid support, so the force always acts towards the rigid support or away from the rigid support. So in case of gravitational attraction, so the force is directed toward the sun, we can say. Okay, in case of solar system. So we see another one. So next one, the characteristics of central forces. So it is a conservative force. So that means work done by the force is independent of the path followed. So force does some work. So the work done by the force is independent of the path followed. Then the force is called conservative. Okay, we can express the conservative forces as negative gradient of potential energy. So in this form, just like this, in three dimensional it is a del. So in one dimension it is minus dv by dr into r cap. So next one, another feature is the angular momentum of the particle remains conserved. If the particle is under central force, so its angular momentum remains conserved as long as it is in central force field. So another feature is torque acting on that particle is always zero. If it is moving in central force field, torque acting on this torque acting on the particle is zero. So the central force is attractive when f of r is less than 0 or it is negative. And the central force is repulsive when f of r is greater than 0 or it is positive. Okay. Uh, Another feature is motion of a particle under central force confines to a plane. If the particle is moving under central force, its path confined to a fixed plane. So plane, especially fixed plane. So we see one by one the proofs of above features. At first we are seeing the conservation of angular momentum under central force. So we are taking central force. We are considering the central force. So we express the central force in this form. F of r bar is equal to f of r into r cap. So the torque acting on the particle. So dl by dt, d by dt into r cross p. So whatever the quantities shown in bold letters are vectors and the remaining are scalars. So it is r bar cross p bar. So it is the differentiation of vector product. Therefore, if we write this, so dr by dt cross p plus r cross dp by dt. So we know that p is equal to mv bar. So we substitute p value here. So in this first term only, so mv cross mv bar plus r bar cross f bar. So the dp by dt is force. The rate of change of momentum is force. So therefore we are writing in this way. So in the next step, so we are writing whatever the f. So our f is now central force. Therefore I am writing f of r into r cap. Okay. So I am writing the r bar as some magnitude small r into unit vector r cap. Okay. So in the next step, it is the cross product of two vectors. The two terms, first term and second term, it is the cross product of the similar vectors, same vectors. So in case of first term, so right, it is m times v cross v. So in second case, it is r cap cross r cap. So the cross product of same vectors is 0. So we are getting zeros in totally 0. So if we see LHS, tau is equal to dl by dt. Okay, that is equal to 0. Here L is equal to constant. So if dl by dt is equal to 0, it indicates that angular momentum L is equal to constant. Angular momentum is the vector. A vector is constant means so its direction is constant and its magnitude is constant. Okay. So in that way, we have shown that the angular momentum under central force remains constant or the angular momentum is conserved. So if we see the first term, tau is equal to 0. So it is showing that so the torque acting on the particle which is under central force is 0. Okay. So we have shown or we have proved the two things. Torque acting on a particle under central force is 0 and the angular momentum remains constant. See the next one. So here the examples for conservation of angular momentum. So motion of a planet in its orbit. So the planets revolve around the sun. So in their paths or orbits, so their motion is so comes under the central force. So their angular momentum is conserved. Okay. Now the scattering of alpha particles by nucleus. So in this case also angular momentum is conserved and man turntable. So in case of man turntable also angular momentum is conserved. So it is the table. If a man is standing just like this by stretching his legs and arms, so the turntable rotates with lesser angular velocity. And if he downs his hand side side to him and he brings his legs near to together. So in this case, angular velocity of the turntable increases and moment of inertia decreases. So in earlier case, moment of inertia is more and angular velocity is less. So, so they change the angular velocity and moment of inertia change such that their product is constant. Since L is equal to I omega, so they change such that their product is always constant. Okay, if omega is less, I is more, and if omega is more and I is less. Okay, we observe this conservation of angular momentum in the case of man turntable. So similarly, we can see the scattering of alpha particles, the heavy nucleus. Next slide. Right. So it is the motion of alpha particle. So if it is the nucleus and it is moving just like this, again we can see. So, so just like this. So it is alpha particle. So as it is approaching, so it moves faster at this stage as it approaches the nucleus and it changes its direction because of the repulsive force, and alpha particle possesses the positive charge and nucleus possesses the positive charge. So because of repulsion it changes its path. Okay, now we are observing the motion of alpha particle. So just like this. So in this case also angular momentum conservation occurs. Right. Now the motion is confined to a plane. That means the motion of a particle under central force is confined to a plane. Okay. In earlier proof, we have seen that L is constant. So it is constant both in magnitude and direction. Okay. So but regarding L is equal to R cross P, it is vector product of two vectors. So by the properties of cross product, so the P can be written as M into V bar. Therefore, we are having R bar cross M into V bar. So these two vectors are perpendicular to L. So R bar is perpendicular to L and V bar is perpendicular to L. So R bar, V bar and L bar are mutually perpendicular to each other. Okay. So that one. Mm, So therefore since L is fixed and R and V confined to a plane which is perpendicular to L bar. So if L is fixed and a plane perpendicular to L bar is also fixed. So in that way R bar and V bar confined to a plane. So the position vector and velocity component of a particle moving under central force field is confined to a plane. We say in that way. Now, aerial velocity under central force remains constant. So, if we take the solar system, it is the sun and a planet is revolving in elliptical orbit. So, if it is the radius vector, right? So, it is the radius vector of the planet, and if we consider a small interval of time in delta t time. So if the planet is initially at point P, after some time delta t it reaches P dash. Okay, it travels delta r bar distance. Okay, Now the position vector is r bar plus delta r bar. Okay, this one. So from this triangle, according the vector addition of triangle, it becomes r bar plus d r bar. Now it is one triangle. So the area of the triangle is delta A is equal to half into base into height. So it is the base and it is the height. So half into 1 by 2 is written here, and base r bar and height delta r bar. Okay. So we divide on both sides with the delta t. So delta A by delta t, that is equal to 1 by 2 r bar cross delta r bar by delta t. As delta t tends to 0, we can write according the definition of limit as delta t tends to 0. So delta A by delta t is equal to dA by dt, and delta r by delta t is equal to dr by dt. So by writing in this way, so that means delta t tends to 0 means within a short interval of time. So this delta r also is very small. So in that case, we are writing with these equations. Now dr by dt is velocity. Okay. So here we are substituting dr by dt is equal to velocity 1 by 2 r bar. Okay. Now dA by dt is equal to 1 by 2 r bar cross v bar. So we multiply and divide with m. So m v bar, that is p bar. So r cross p is again angular momentum vector L bar. So therefore L bar by 2m we are getting here. So from this, so dA by dt is the area, dA is the area swept out by the radius vector in interval of time dt. So therefore dA by dt is the area swept out by the position vector or the radius vector of the planet in interval of time dt. So that is equal to L bar by 2m. So since L bar is constant and L bar by 2m mass of the planet is also constant, so the dA by dt is equal to constant. That means the radius vector sweeps out equal areas in equal intervals of time. So that means as it approaches the shorter distance, it moves faster. As it goes the longer distances, that means if the position vector is longer, so here it moves slowly. So in that way, so in equal intervals of time, the radius vector covers equal areas. Okay, it is about aerial velocity and the central force is remain constant. So here we have used the property of central force. L is constant. Since L is constant and aerial velocity is also constant, so this dA by dt is also called as aerial velocity. Okay, thank you. So in this lecture we have seen. So in this lecture we have seen central force. What is the central force? A force which always acts towards a point or away from a point is called central force, and it can be expressed as some function of position f of r into r cap, the unit vector along the radial direction. Okay, the examples for central forces is the gravitational force of attraction between two masses, and the electrostatic force between two charges, and the force in mass spring system. Okay, next one, the features. The features of central forces are the characteristics of central forces. So the central force is conservative force. We can express it as negative gradient of potential, and the central force is Under central force, angular momentum of the particle remains conserved, and under the central force, torque acting on the particle is always zero, and central force is attractive when f of r is less than 0 and repulsive when f of r is greater than 0. The motion of a particle under central force confines to a plane. So we have seen these points. Now, so in the case of conservation of angular momentum, the motion of the planets is example for conservation of angular momentum, and the scattering of alpha particles by heavy nucleus is also an example for conservation of angular momentum, and the man turntable. Right. So thank you for watching.